Welcome to UBG Bytes, where we break down the latest in tech and security into bite-sized chunks. Today, we're digging into a really interesting paper from DeepSeek AI. They've been looking at how reinforcement learning, RL, can give a serious boost to the reasoning capabilities of large language models, LLMs.
Yeah, it's pretty cutting edge stuff. They've trained a couple of main models, DeepSeek R10 and then DeepSeek R1, and they're really pushing the envelope on what these models can handle in terms of complex reasoning.
Exactly. And for you listening, if you're in security research, maybe pen testing or vulnerability management, these aren't just abstract tasks. We're talking benchmarks that are highly relevant things like analyzing code, complex logic, even tackling real software issues.
That's right. This moves beyond just, generating plausible text. It's about getting these models to actually think in a structured way, break down problems, follow logic, maybe even catch their own mistakes along the way.
In this paper, it's straight from Archicno, lays out how they used RL to train and unlock that.
And the key findings are quite something. First, they found that pure RL, kind of surprisingly, could get these reasoning behaviors to emerge almost on their own. Then, they refined that. Built a more complex, multi-stage approach using curated data in RL, creating models that actually stand up pretty well against some top-closed models on really tough benchmarks.
Plus, they found ways to sort of distill that reasoning power down into smaller models, which is huge for practical use.
So let's start at the beginning. Their first major experiment was DeepSeek R10. What's really fascinating here is that it was a test of pure RL. They took a base LLM, applied RL directly, and totally skipped the usual supervised fine-tuning, the SFT step that most models go through first.
Whoa, okay. No SFT. That's definitely not the standard playbook. Usually you start with SFT on human examples to teach the basics, right? Format, style, why skip it?
It was deliberate. They wanted to test a hypothesis. Could reasoning ability actually emerge just from the reward signal, just incentivizing the correct outcome on complex problems without ever explicitly showing the model how to reason step by step via SFT data?
Ah, okay. So could the model learn the process purely by optimizing for the result?
Exactly, like giving a student a tough math problem and the answer and saying, figure it out without any worked examples.
Okay, I get the concept. How do they actually implement the reward part efficiently? RL at this scale can be computationally brutal.
Good point. They used a framework called GRPO, Group Relative Policy Optimization. The clever bit about GRPO is its efficiency. Instead of needing a whole separate, often huge critic model to estimate reward values, GRPO figures out a baseline by comparing outputs within groups of generated samples. It's a smarter way to get that essential feedback signal without the massive overhead.
Got it. Efficient rewards. And the rewards themselves for R10, you said they kept them simple.
Very simple, yeah. Rule-based, mainly. Two kinds. First, accuracy rewards. Pretty straightforward. If the problem had a clear right answer, like math or coding problems with test cases, did the model get it right? Often checked within specific output tokens. Second, format rewards. Even simpler. Just rewarding the model for structuring its output correctly, like putting its thinking process between think and think tags.
And they specifically avoided complex neural reward models at this early stage.
Right. To sidestep potential issues like reward hacking, where the model finds a loophole to get the reward without actually doing the task properly, keeping it simple let them isolate the effect of the pure RL signal.
Makes sense. Control the variables. And what happened? What emerged from this pure RL approach?
It was pretty remarkable, actually. Over thousands of RL steps, starting from that base model with zero prior reasoning SFT, DeepSeek R10 started developing complex behaviors all on its own.
Like that graph they showed, the average length of the model's output, particularly the reasoning part inside the think tags, just steadily increased during training.
Exactly. The model wasn't explicitly told think longer. It learned implicitly that spending more internal computation, more steps exploring the problem, often led to the correct answer, and therefore a higher reward.
So it learned to allocate thinking time dynamically.
Precisely.
Yeah.
And alongside that, other behaviors we associate with reasoning started appearing. Things like reflection, self-verification. The model would generate a step, then seem to pause or reconsider, maybe try a different path if it got stuck.
They had that amazing example, didn't they? The aha moment. from an intermediate model.
Oh, yeah, that was wild. It was working on a math problem, and its internal trace literally included text like, wait, that's an aha moment I can flag here. Let's reevaluate this step by step.
It's like the model was talking to itself, signaling a need to rethink.
For the researchers, that was a huge sign that RL alone, just rewarding the outcome, could actually teach these sophisticated problem-solving strategies.
And did this strategy translate into better performance?
Absolutely. DeepSeek R10 showed a massive improvement on benchmarks like AIM 2024. That's a tough competitive math exam. Its pass at one score, getting it right first try, jumped from around 15.6% baseline to 71.0%.
Wow, that's a huge leap.
And get this, if they used majority voting across 64 generated samples, it could hit 86.7%. That actually surpassed OpenAI's 010912 model on A, giving enough samples.
Just from outcome-based RL.
Yeah.
Incredible. But R10 wasn't perfect, right? It had some issues.
Correct. Despite the impressive reasoning emergence, the output quality wasn't great, readability was poor, and it had this tendency towards language mixing, not ideal for practical applications.
So the pure RL experiment proved a point, but wasn't the final product. They needed refinement, which brings us to DeepSeek R1.
Exactly. They took the core lesson, RL drives reasoning, but built a more sophisticated multi-stage pipeline to create DeepSeek R1, aiming for both high performance and usability. And this pipeline started differently. They used what they called a cold start.
Okay, what's a cold start in this context?
Unlike R10's pure RL beginning, R1 started with a small dose of initial supervised fine-tuning. They used a limited set of high-quality, human-written, long chain of thought examples.
Ah, so SFT did come back into the picture, just strategically at the start.
Precisely. Just enough to give the model a stable foundation, prevent some of the chaotic training starts they might have seen otherwise, and crucially, introduce a readable output format right away. This data often included both the reasoning and a summary marked by special tokens.
Okay, so establish a good, readable baseline first with a little SFT. Then what? Build on that foundation.
Then came the main reasoning-oriented RL phase. Similar scale to R10, hitting those hard reasoning tasks, coding, math, science. But this time, they added a twist to combat the language mixing issue.
How do they address that?
They introduced a language consistency reward alongside the usual accuracy reward.
So a reward for being right and reward for sticking to one language.
Exactly. They noted it involved a slight trade-off, potentially sacrificing a tiny bit of raw accuracy for much better readability and usability. The final reward signal was a combination of both accuracy and language consistency.
Makes sense. No point being brilliant if nobody can understand you. We use stage 3.
Stage 3 was clever, rejection sampling and SFT. After that first big RL stage finished, they used the improved model to generate a lot of potential solutions, especially for reasoning tasks. Then they used automated rules checking for correctness, format adherence to select the best generated outputs. This is rejection sampling. They curated around 800,000 high-quality samples this way.
Okay.
And this curated dataset, generated by their own RL-improved model, was then used for another round of supervised fine-tuning. They also mixed in data for other capabilities like writing and Q&A here.
So they use the model to teach itself, essentially, bootstrapping a better SFT dataset from the RL stage's output.
You got it. It leverages the RL gains to broaden capabilities through SFT, and then the final stage, all scenario RL.
Another RL round.
Yes, but this one was broader, aimed at aligning the model with general human preferences, helpfulness, harmlessness across all kinds of prompts, not just reasoning, while still refining the reasoning part. They used rule-based rewards for reasoning checks, but brought in neural reward models trained on preference data for that general alignment piece.
Okay, that's a complex pipeline. Cold start SFT, then reasoning RL with consistency, then SFT on model-generated data, then broad alignment RL. Quite the process. How did DeepSeek R1 perform after all that?
Extremely well. They showed it's very competitive, often comparable to strong models like OpenAI's 011217, especially on the key reasoning and coding fronts. On AIME 2024, R1 got 79.8% pass at 1, slightly ahead of 011217 to 79.2%.
Nice.
On Math 500, another tough math set, R1 hit 97.3% pass at 1, again just edging out 011217 at 96.4%. Coding performance was solid too. Code Forces percentile, R1 was at 96.3%. R1 scored 65.9% versus 63.4%.
And the one that really jumped out for our audience, SWE Bench.
Right. SWE Bench Verified Resolved. This tests the ability to fix real bugs from GitHub issues. DeepSeek R1 managed to resolve 49.2% of them.
Almost half.
Yeah.
It's genuinely impressive for automated bug fixing. Think about the implications for vulnerability patching or code analysis.
It's a significant result, absolutely. And R1 also showed gains over their previous DeepSeek V3 on knowledge benchmarks and performed well on writing and QA tasks, too.
So R1 is a beast. But big models are often hard to deploy. Did they tackle making this reasoning power more accessible?
They did, and this is the distillation part, which is really promising. They took the capabilities of the big DeepSeek R1 and worked on transferring them to smaller open-source models based on Qwen and Llama architectures.
How do you distill something like complex reasoning? More RL.
Actually, no. Surprisingly simple. Method-wise, they just used supervised fine-tuning again. They took that 800K curated dataset, the one generated by DeepSeek R1 during its training, and fine-tuned various smaller base models from 1.5B up to 70B parameters using only that dataset. No extra RL on the small models for this step.
Just SFT using the big model's good outputs. Could that really transfer the reasoning skills effectively?
Apparently, yes. The results were quite striking. Their DeepSeek R1 Distill Qwen 7B model, only 7 billion parameters actually outperformed giants like GPT-4o and Claude 3.5 Sonnet on those math benchmarks, AIM and Math.
Hey, seriously, a 7B model, just fine-tuned on generated data, beating GPT-4o and Claude 3.5 Sonnet on math reasoning.
That's what their results show. AIM's score was 28.9%, Math was 83.9% for that 7B distilled model. It's a massive pointer towards efficient capability transfer.
That changes things. You don't necessarily need the absolute biggest model if you can effectively distill the critical capabilities.
Exactly. Their other distilled models showed similar trends. The 14B beat a 32B model. The 32B and 70B significantly outperformed OpenAI 1 Mini. And their key comparison found that distilling from the big R1 to a 32B model was much more effective and cheaper than trying to run the whole multi-stage RL process directly on a 32B base model.
That's a crucial insight for anyone thinking about deploying capable models economically. Leverage the big training run, then distill efficiently.
Right. Now, it's also important to talk about what didn't work so well. Research is learning from failures, too. They shared some attempts that didn't pan out.
Always valuable. What kind of approaches did they try that hit roadblocks for this kind of large-scale RL?
One was using process reward models, or PRMs. The idea makes intuitive sense. Instead of just rewarding the final answer, reward each correct step in the reasoning chain.
Yeah, guide the logic flow directly. Seems logical. What was the problem?
Scalability and verification. Defining correct steps universally for diverse, complex problems is really hard. Automatically checking every single intermediate reasoning step is computationally expensive and complex. Plus, it was still vulnerable to reward hacking gaming the step rewards without real understanding.
So, good idea in principle, but tough to implement reliably at scale for training.
They felt it was maybe better for simpler verification or just re-ranking outputs, not as the core driver for the RL training itself.
Okay. What else did they try?
Monte Carlo Tree Search, MCTS, borrowed from game AI like AlphaGo, trying to adapt it for token generation. The idea was for the model to explore different generation paths, like looking ahead a few steps, to improve the final output during inference.
Like the model running simulations of its own writing process.
Sort of, yeah. But two big hurdles. First, the search space in language is astronomically larger than in board games. Second, and more critical, training an effective value model, a component that can accurately judge the promise of an intermediate sequence of tokens, proved extremely difficult for language. Without that guidance, MCTS didn't offer the expected benefits.
So, lessons learned. PRMs are tricky to scale for training, and MCTS from games needs more work to adapt effectively to the nuances of language generation.
Exactly. And they were also upfront about DeepSeek R1's current limitations. Areas for future work. One is prompt sensitivity. R1 performs best with zero-shot prompts where you clearly state the desired format. It doesn't do as well with few-shot examples baked into the prompt.
Good to know for practical use.
Language mixing, while better than R10, can still crop up, especially outside English and Chinese. General capabilities, things like multi-turn chat, function calling, complex roleplay, aren't as strong as their more generally trained DeepSeek V3. R1 is more specialized for reasoning.
Specialization has trade-offs.
And software engineering tasks. Despite that great SWE bench score, the evaluation complexity for code makes RL training slower in that domain compared to math or competitive coding. So while good, they see more room for RL-driven improvement there in future versions.
Okay, clear limitations and future directions. Now, that multi-stage training pipeline for R1 was quite involved. You mentioned cold start, reasoning RL, SFT from rejection sampling, all scenario RL. We need a way to remember that, maybe an acronym.
Yeah, we could definitely summarize it. How about CRSA?
CRSA. Okay, break it down.
C for cold, start that initial stabilizing SFT. R for reasoning-oriented RL, the main RL phase targeting hard problems. S for SFT from rejection sampling, using the model's own improved output to generate better training data. And A for all scenario RL, the final broader alignment stage.
CRSA, cold start, reasoning RL, SFT from rejection sampling, all scenario RL. Got it. That captures the core stages that built DeepSeek R1.
So thinking about this from your perspective, you're a pen tester looking at code, a researcher analyzing vulnerabilities, managing security posture. What does a model like R1 mean? Its performance on coding, on SWE bench, its reasoning. These could become incredibly powerful analysis tools. Imagine automated systems that don't just find syntax errors, but understand logic deeply enough to spot subtle flaws or even suggest exploit chains.
Using them as tools? Absolutely.
Yeah.
But the flip side, what happens when adversaries leverage models with this kind of reasoning power?
That's the crucial question. Could these models themselves become targets? Are there new ways to attack systems through these reasoning models? Could their prompt sensitivity be exploited? Their internal reasoning processes, do they have blind spots?
Right. It opens up a whole new front in the security landscape, doesn't it? Both for leveraging the tech and defending against its misuse.
Definitely. The intersection of advanced AI, reasoning, and security is heating up fast. Lots to explore, lots to figure out.
A fascinating area to watch, for sure. Both the potential and the risks are significant.
That's all for this bite of InfoSec Insight. Until next time, stay sharp, stay curious, and keep breaking things responsibly, of course.